Okay, so let's look at an example now of finding the volume of a solid. In this case, our solid is bounded by the planes x equals 0, y equals 0, z equals 0, and an additional plane 2x plus 2y plus z equals 4. So we're going to want to graph this, again, just to try and get a sense for what it is. The first part of this we can grab here that says x, y, and z all equaling 0. This is telling us something about where we're located. So this is oftentimes indication that we're going to be in the first octant. So we're restricting ourselves to just positive values often when we list these planes out this way. So let's see if we can sketch a graph of this just to kind of get a feeling for what's happening with this scenario. So we're going to need ourselves a coordinate system. There we go. And let's start looking at what we've got. Again, we've got the planes x, y, z equals 0. So these are our coordinate planes. And now it's just this additional plane here that we see that's going to cut through our coordinate planes at some angle. The best way to visualize these often is to just plot up where the x, y, and z intercepts are for these, which is pretty easy to come by as well, which makes it work pretty well. So let's go after those. So for this, the x-intercept is what we get when we take y and z equal to 0. So if we do that, we see that we get x equals 2. The y-intercept is when we take x and z equal to 0. And you see we get y equals 2. And then for the z-intercept, it's the same story. We take x and y equal to 0, and we get z equals 4. Okay, so now we've got those. Let's go ahead and plot those up. I'm just going to approximate where these things would be. Let's call this 4. Let's call this 2. And let's call this 2 as well. All right, so now you've got your intercepts plotted. And again, the best way to visualize these types of planes cutting through is just to connect them all up with a little triangle. And that will give us a pretty good idea of what this surface is going to look like as it cuts through. Last one. Again, it doesn't have to be perfect, just good enough for us to get an idea for what that plane's doing. So obviously this plane extends infinitely in all three directions here, but in terms of visualizing it, we can now see that it sort of cuts through at this angle. Here's the surface of that plane, kind of cutting through our coordinate planes as it goes sort of up and back. Okay, so now we've got a good sense for what it's doing. Now we've got to come up with the volume of this thing, so we've got to come up with some bounds. If you kind of visualize this, then we've got this plane being the upper surface. The lower surface then is going to be the xy plane down here. So that's setting up our range of values for z. And in fact, we can even solve out our plane here for z to help us out a little bit here in a minute. So 4 minus 2x minus 2y. And of course, the coordinate plane xy is just where, again, z is equal to 0. So now we've already got our range of values for z. Z is bounded between 0 and the plane 4 minus 2x minus 2y. Okay, so we've got that. So that's our surface to surface. Now we've got to take a look and figure out how we can set up the region of integration down here. Right, this is going to be the next step. So what does that look like? Well, again, it's probably useful for us to graph this. I'm going to stand the xy plane up so we can take a look at what it looks like, which means that we're going to need another coordinate system. So let's grab that. Okay, there we go. And what we're going to do is we're going to take this region in the xy plane, and we're going to redraw it over here on our new axis. So we're going to put in the 2 points of intersection, which were at 2 and 2. And then we want to figure out what this line is doing here. Remember, this is our region that we're taking a look at, so we can figure out what's happening with the rest of our limits. So there's a line of intersection between the plane and the xy plane that looks something like this. And the reason why we need this is so that we can look at this region D. This is our region that we're talking about up here. So now let's figure out what the bounds for the region D are going to be. We're going to run this. I'm going to do this from function to function this way, and then we'll go constant to constant along the x's. So what I really need then is the equation of this line, and I think it should be pretty apparent. We've got it intercepts at 2 and 2, so its slope is -1, and its y-intercept is here at 2. So the equation would be y equals -x plus 2 for that line. So y then is going to go between those two functions, y equals 0 for the x-axis, and the line. So that would be our range of values there. 0 less than or equal to y, less than or equal to -x plus 2, or 2 minus x if you prefer. So here's our surface to surface, here's our function to function. Now we just need to grab the constant to constant. X is going to go between 0 and 2. 0 less than or equal to x, less than or equal to 2. And there you have it. All three of our limits are set, and we can set up our triple integral. So we want the triple integral. Again, working from the inside out, surface to surface, the z's are going to go from 0 to 4 minus 2x minus 2y. Y is going to go from 0 to minus x plus 2. And x is going to go from 0 to 2. We're integrating just the function 1, dv. In this case, v is rectangular, so we're going to use our typical dz, dy, dx in that order, since that's how we set them up. So there you go. There's our integral. Now the integration here is not that challenging, so I'll let you go ahead and finish that out.